This is Aaron from the Caradrone team. This is regarding the flight computer subsystem. The C# application that's up on the computer screen, this is what's called the Caradrone control panel. This is the software that sits on the PC. It is connected via USB to the Caradrone. Let me show you this right here. Where is that cable? USB cable connected to the back of the computer. Is going into the flight computer there. It is actually pulling data from the flight computer. This is part of the reason why that USB cable is there is it allows us to basically debug the flight computer and to pull telemetry from it. So yeah, that's what's going on. That little right there, that sensor right there, that's the altimeter. The gyroscope is under that mess of wires. Is actually sitting next to a couple of ESCs, but you can kind of see it here. It's got the blue, white, red, yellow, black, and orange cables going to it. Basically, that right there is going down into the flight computer. On this side, we have the radio receiver. It is connected direct to the flight computer. We're going to do the RC subsystem test, input test, to show that the flight computer does correctly interpret the RC input. So let's go back over to the computer. This is the controller. If we look here, basically we have one part that's showing the input. That is basically the raw data coming from the controller, the RC receiver. There's flight data, which is current altitude. Right now it's hard set to one standard atmospheric pressure at sea level for the reference. So, and the pressure today is a little bit on the low side, so the altitude is showing a little bit high. It's also showing the current temperature in Kelvin. The orientation, that's the basically what's going on is the first column is the absolute orientation according to our gyroscope. There's data coming from the gyroscope in 9 degrees of freedom, 3 degrees of freedom for gyroscope, 3-dimensional accelerometer, 3-dimensional magnetometer, and it's going through a data fusion algorithm. This is the output from the feedback loop. It's showing raw, pitch, and yaw. The second column is the output from our PID controllers. The motor statistics, this is what our control algorithm says the motors should be throttled at. In case you're wondering, that negative number, the ESCs would have filtered that negative number and interpreted that as a 0, essentially. Down below is the data input. We had some trouble connecting it. One of our subsystem tests was the debug test, basically where we give it a self-test command, which I'm going to do right now. And I cannot type. Essentially, what this does is this sends a command to the flight computer. FC stands for flight computer, and then we send the command, the subsystem test. It was just to send the string back, there shall be wings, which it did. There's no extraneous data, no extra data, and it is, as you can see, is the exact string. So that subsystem is passed. Now the RC input test, basically what we do, as you can see, according to the PC, the throttle is at 3% right now, so hardly anything at all. Okay, let's get the camera to focus. Oh well, it's at 3%. But if I move the input on the controller, we can see it changing. Yeah, I can actually move this around all day long, pretty much. This is yaw. Pretty much for yaw, I'm just adjusting it like this. This is pitch. It's capped out at 15 and negative 15 degrees on the pitch. Basically pitch is this one right here. Let's get the camera to focus here. This is kind of, there we go. Okay, there's roll right there. On the controller, roll is this stick being shifted sideways, as you can see. So it is correctly interpreting RC input. There's also the cargo switch right here. As you can see, it's correctly interpreting that as well. Come over to orientation. I'm going to show you what happens when you give it any kind of input on that. As you can see, the PID controller output changes based on the input that I give it. Same with roll, same with pitch, same with yaw. Now, let me explain this one. It shows that the pitch is off a little bit. That's a little error that's easily fixed just by inserting an offset value. I'm using it to my advantage in this case just to show you what happens when it's at a pitch. As you can see, the computer thinks it's at a -8-degree pitch, which may or may not be true because that table may not be level. And it's showing the PID controller output wants to correct by 8 degrees. If I pitch down, it goes down to -6. It doesn't actually max out because it detects that's at an angle and it wants to correct that angle first. And then it's going, if I pitch forward, it goes to the full 15 degrees. Same with roll. Roll is pretty much there. It's capped at 15 degrees. Yaw is actually capped at 30 degrees per second. As you can also see, as I'm changing things, we're seeing motor speed changes down there. That's the output from the plant. So basically what it is motor 1 through 6. Motor 1, 2, 3, and 4 would be the 4 motors as if this was a quadcopter. So basically the starboard side motors, if this was a quadcopter, would be motors 1 and 3. The port side motors would be 2 and 4. And then for the motors 5 and 6, which constitutes a hexacopter, 5 is the port side, 6 is the starboard side. And if I adjust the throttle, they all go up evenly. If I set the throttle, let's say about 50%, and then do a yaw, you should see motors 1, 2, and 6 spin up. Same there. So that's yaw. This is roll. Roll, you should only be seeing changes in motors 5 and 6. And roll is a little bit funny. I might look into that. And then, of course, this is pitch. I should only be seeing, I believe, the even number ones. Yeah. So this is a pitch forward. Motors 2 and 4 go up. Actually, I'm sorry. 2 and 4 are not the port side. 2 and 4 are the back side, and 1 and 3 is the front side. I had that wrong. That's a pitch forward. As you can see, the back side motors throttle up. If I pitch back, the front side motors pitch up. If I roll, of course, we got differences in motors 5 and 6. Now, let's show you the cargo. I'm rambling on this. This is going to be like a 10-minute long video. As you can see, the cargo crate is currently attached. And of course, the debugger is attached to supply and power. I'm going to show you this. If I flip the switch, that one did not go. That's a friction thing. I'll show you this one. There we go. And it's correctly interpreted. And there you go. And that right there, my friends, is a flight computer.